So when we define the row space, so just as a reminder, for those of you who watched the video, but for those of you who didn't, well, now you get to see it again. So the row space of A is, okay, the non-zero rows of A in the REF of A. So it's the non-zero rows of A in the REF of A. It forms a basis for the row vectors of A. Okay, so it's going to form a basis for the row vectors of A. All right, what we're going to see is, if you remember, it doesn't mean that it's going to be forming a basis for, say, for example, Rn or Rm, right? Not necessarily. We'll see this in just a moment. But what it will do is it forms a basis for those row vectors. And then it's going to allow us some context, right? It's going to allow us to kind of like compare, right? Compare that basis that gets generated against, say, for example, Rn or Rm or P2R or whatever the vector space that we're working in, okay? So that's what our row space is, okay? And then the column space of A, all right, which we call Colspace, is how we denote it, Colspace A, is the basis for the column vectors of A. And we've talked about, from a theoretical standpoint, we've talked about this call space of A before when we were talking about span. When we talked about like what happens if you end up with a vector that's a linear combination of the other vectors in the matrix. And when that happens, what you end up with is you end up with an extraneous vector, a redundant vector, and so we can remove that. And when we remove that, what we end up with is we're going to end up with a call space. Okay. So like, let's take, for example, take an example. Okay, we'll let A equal 1, 1, 2, 0, okay, -3, 1, 1, and 1, -2, 3. So, all right, so just head back here. Let's take this example for A. And it's 1, 2, 0, -3, 1, 1, 1, -2, 3. And so the REF of A is going to end up equaling -3, 1, 1, 0, 7/3, 1/3, and 0, 0, 25/7. So that's the row reduction, REF of A. All right. So we start out with the row space of A is going to be the non-zero rows of A in REF, and it'll form a basis for the row vectors of A. So my row space, the row space of A, and I'm going to write them in this case as column vectors, is going to be -3, 1, 1. Notice that they're row vectors. So I'm going to take along the row, comma, 0, 7/3, 1/3, comma, 0, 0, 25/7. And that's in my brackets. Now let's think about this from the standpoint of the call space of A. All right, we said call space of A is a basis for the column vectors of A. So that means that we need a set of linearly independent vectors. Okay, we want a set of linearly independent vectors. So tell me, anybody out there, let's take a look at this set. So can anybody tell me what vectors in A are linearly independent? What set of vectors in A are linearly independent?
In row space A?
No, in A, which of the vectors in A that are linearly independent, the column vectors of A that are linearly independent?
The column vectors of A.
Okay, Which ones, Raphael? Can you name them?
1, -3, 1, 2, 1, -2, 0, 1, 3.
Okay, great. Why is that the case? Why are they linearly independent?
I'm just going off of the videos.
Okay, well, let's just think about though. Okay, so it's a good question. Why is it that we know that the three column vectors of A are in fact linearly independent?
Well,
I mean,
I
like,
think
why does that work?
if we look at the REF, it's in the upper triangular form, so we can calculate
Okay,
determinant, and it's not 0, so that means it's
okay,
invertible. And if it's invertible,
means
then
A is invertible.
yeah,
Okay,
if it's invertible,
and
then
so
it's linearly independent, right?
okay, then the set of column vectors are linearly independent. Yes.
Okay.
Okay, great, good. All right. So we've got a couple ways to actually make that determination. So the answer is yes. All right. This set of vectors ends up being linearly independent. And how we know that the set of vectors is linearly independent is because in a row reduction, REF of A, okay? So if you imagine what's going to happen, our REF of A is going to do this kind of thing, okay? Our REF of A will row reduce down to the identity. And the reason why we know that is because, I mean, basically it's what Alex said, okay? And there's a lot of reasons actually, but one of the reasons we might say that is because we know, right? So the determinant of A will not equal 0. How do we know the determinant of A is not going to equal 0? Well, we've got, this is in upper triangular form, okay? And in upper triangular form, what we end up with is we end up with the determinant is equal to the multiplication of the diagonal, right? Okay. And so there's no way that we're going to end up, when we take the determinant of A, right, that we're going to end up at 0, right? That's just the case. In addition, if you think about like row reduction, right, if we went in and we row reduced, REF of A, okay, then what we'd end up with is we'd end up with this, we'd end up with the identity matrix because there's a pivot. We got a pivot in every single column here. Okay, we have a pivot in every single column, and we just know that we can turn these all into ones, and then we're just going to have to row reduce above. So we know that we're going to end up here at REF of A. Okay, so consequently, those three vectors, 1, -1, -3, 1, 2, 1, -2, and 0, 1, 3, are going to end up being linearly independent, okay? So what we could say is, since, okay, REF of A, right, equals the identity I3, then A is invertible. And if you remember from earlier on in the week, so the column vectors of A are linearly independent. So the column vectors of A are linearly independent, right? And because the column vectors of A are linearly independent, all right, thus the column vectors form a basis. Okay, so they form a basis because they're linearly independent. Now, do they form a basis for Rn, or excuse me, in this case, R3? Do they form a basis for R3? Any ideas? Put your answer in the chat if you're like, yeah, they form a basis for R3. No, not so much. And think about what it means to be a basis. Okay, so do they form a basis for R3? All right, there are three components, so we know all the vectors are in R3. That's true. Okay, think about what it means to be a basis by definition. By definition, a basis is what?
Is it because it's invertible?
Well, that's true. That's exactly what that's going to be the case. But I want you to think about what a basis is. A basis is, by definition, what? Go look it up, everyone. You have to.
It has to span the vector space and be linearly independent.
Yes, it has to span the vector space, in this case R3, and the set has to be linearly independent for it to be a basis. So the question is, first, all right, do these vectors span R3? These three vectors span R3? Let's see. What do you think, On? Do these vectors span R3? These three vectors, the vectors of A, let me be more clear. The vectors of A, will they span R3? This is when the crickets are coming out. Yeah, they're going to span R3. Okay. And bunch of reasons why we're going to say that they're going to span R3. One, there's three of them, and there are three linearly independent vectors in R3. Okay. So let's write this down. Okay. There are three linearly independent vectors in R3. So we've got three linearly independent vectors in R3. Okay. Each of these vectors, the set of vectors, is linearly, oh, we just said that. The set of vectors is thus spans R3. Think about it from this perspective, from a geometric perspective. Linearly independent, when we talk about linearly independent, what we're basically talking about is that the vectors are all in different directions, right? There's no like redundant directions. So like you've got one vector, and then you find another linearly independent vector, and they form a plane. And then the third vector, because it's linearly independent from the first two, is off of that plane, right? It moves up off of the plane. And so consequently, what we end up with is we end up with three linearly independent vectors. They give us all of R3. We can go anywhere within R3 utilizing those three vectors, okay? And thus it spans R3. So the column space, okay, of A forms a basis for R3. So it forms the basis for R3. So the call space of A, all right? So call space of A equals, okay? On the one hand, we can say that the call space of A is going to equal 1, -3, 1, 2, -1, 2. I got it sitting right here on my notes. Is going to be 1, -3, 1, 2, 1, -2, 0, 1, 3. It's those three vectors. And those three vectors, because they are a basis and there's three of them, they're going to be R3. They are, in fact, all of R3. Three linearly independent vectors in R3 gives you R3. All right, so how about this though? Take a look at the row space. So now the row space, okay, is a set of three vectors, all right? And it's a basis made up of the row vectors, the non-zero row vectors. All right, here's a question. So is the row space also R3? So look at the row space up there. Three, in this case, a basis made up of three vectors in R3. Are they going to be R3? is the row space of A equal to R3. Okay. You want to give it a shot? Oh, whatever. Yeah, it is. Yes, totally. Okay. Yes. Yes, because we have 3, okay, linearly independent vectors in R3.
Oh,
So they
Professor,
form a basis.
what
Yeah,
does
what's
it
up?
what does it mean when you put equals R3? Does that mean like it's a basis or spans or?
Oh, okay, got it. Yeah, what I'm saying is that it forms a basis for R3. Okay, so actually, and what we might even want to say, yeah, that's a good question. All right, that's what I mean.
All right,
So this is basically saying the call space of A is a basis for R3. Good question. All right. On the other hand, I mean, like if we wanted to, we could write it like this, the span, but people don't. I mean, like that's probably why I didn't, because people just don't write things like this. It's, I guess when I write things like that, what I really mean or is this. Like say, for example, the span of the call space of A, okay, is equal to R3. So all of the linear combinations of that basis that's called the call space of A, okay, is R3. But we just say call space of A equals R3. Done. That's it.
Okay. Cool.
Okay. Sorry. All right. What about this? Let's say, for example, let's take a look. Now, I'm going to define something here. I'm going to define a little bit extra here. So to find the call space of A, so the call space of A is a basis. All right. It's a basis for a subset of our vector space V. Okay. And it's made up of the linearly independent column vectors of A. So to find the call space of A, row reduce A to REF of A. Okay, so we're going to row reduce A to REF of A. For each column, for each pivot, excuse me, so for each pivot in REF A. So that is non-zero leading 1, right? Okay, so each pivot in REF A, the corresponding column in A is a column vector in call space of A. All right, so let's just do we'll do a couple examples of this. All right, okay. Oop. So let's say, for example, that we have, we'll let A equal -1, 3, and then 2, -6. Okay, so we'll have -1, 2, 3, -6. So that's A. All right, and what we'll do is we'll take the REF of A, or yeah, we'll take the REF of A. All right. Okay. And that's going to end up equaling -1, 2, 0, 0. You can check that if you want, but you can probably see that that's going to be the case. All right. So now the row space is the non-zero rows of A. Row space of A equals the non-zero rows of A. So of REFA. And so that row space is going to equal, okay, -1, 2. So that's the row space, is -1, 2. All right. Now, if we look in the row reduction, there's our pivot. Our pivot is in the first column, right? And in fact, it turns out, if you can kind of interpret this, that the second vector, 2, -6, is in fact linearly dependent to the first column, right? The two of them, they're scalar multiples of each other. So they're basically redundant vectors, okay? -1, 3, right? Notice -1, 3 equals, right? -2, -1/2, excuse me, times 2, -6. So they're scalar multiples of each other. So this is a linearly dependent set. And so the vector 2, -6 is redundant, right? Because it's basically -1, 3, okay, just written differently. So my call space, I'm going to eliminate that one, right? I'm going to just take the one where I have a pivot, right? -1, 0. So call space of A, okay, is going to then equal -1, 3. So I'm going to go back to the original matrix A, and I'm going to plug in my vector. Okay, so I'm going to plug in my vector there. Questions? We'll do a couple more examples of this. Then we'll do some rank nullity. And all right, welcome back. Okay, so let's take, for example, so we're going to let A equal. So we'll find, what we want to do is we're going to find the row space of A and the column space of A. Okay, so we're going to find the row space of A and the column space of A. All right, and let's say, for example, we take this. We've got 2, -1, 3, 4. Okay, 1, -2, 1, 3. Okay, and 1, -5, 0, 5. All right, so that ends up being our matrix A. And so if I look at this, one of the things that I know right off the bat, okay, is that my column space, one of these vectors is going to end up being redundant. It's going to be a redundant vector. The set of column vectors is in fact linearly dependent. So I'm not going to need at least one of them. Now there may be more than one that I don't need, but at least one of those is going to be unnecessary. So that's the first thing that I want to notice, right? I've got 4 vectors in R3. So 1 will not be necessary. Okay, right? Too many vectors in R3. Okay. In addition, right? Notice the row vectors of A. Okay, so that's 1. The row vectors of A, they're in R4. So the row vectors of an A are in R4. Huh. Interesting. So in this case, like in the last example that we had, the column vectors were in R3 and the row vectors were in R3. But in this case, right, okay, the column vectors are in R3 and the row vectors are in R4. So call space of A will be a subspace of R3, right? Because its vectors are in R3. And in addition to that, and row space of A, or row space of A, will be a subspace of R4. because the vectors are in two different spaces. Notice row vectors, we have 1, 2, 3, 4 values for the row vectors, okay? And the column space is only 3. Now, here's the question, all right? Will the row space of A equal R4? Will it actually equal to R4? Or in other words, be a basis for R4? So will the row space of A actually be a basis for R4? Let's think about why or why not. It's the row space of A, right? So if we think about the basis vectors for A, for the rows of it, the basis vectors made up of the rows, non-zero rows of REFA, all right? Is that going to be, in fact, all of R4? Answer is no. No, it won't. There's not enough of them. The amount of row vectors that we could have in REFA is 3. We have a maximum number of 3 row vectors in REFA, right? Because there's only 3 row vectors in A. You need 4 row vectors in R4 to give you all of R4. Does everybody catch that? I want that to be really, really clear, okay? To give me all of like a vector space, a 4-dimensional vector space, I need 4 vectors. To give me all of a 3-dimensional vector space, I need 3 vectors. To give me all of a 5-dimensional vector space, I need 5 vectors, okay? So consequently, if I don't have that many vectors, I'm not getting that entire space. That's never gonna happen, right? That's a not gonna happen ever kind of thing, okay? So in this case, the answer is no. There are only 3 vectors, there are 3 row vectors in A. So the max number of non-zero rows in A is 3. Done. So yeah, so the answer is no. Okay, now let's go in row reduce. Just take it down to REF of A. Take a minute to do that, throw it in your calculators, throw it on your computers.
Did you say the REF or the RREF?
In fact, when we're finding the row space and the column space, we're only going to need the REF, the row echelon form. All right, so that's our row reduction. Take a second as you're finishing everything up. So there's our row reduction. So if I wanted to create, let's say, for example, we start out, let's do the row space of A, and that's the set of non-zero rows in REF of A. So it'll end up being 2, -1, 3, 4, comma, 0, -9 halves, -3 halves, 3. And so what I'm going to do, notice that we've got those two. Those are the 2 non-zero row vectors of REF of A. Okay. And so I'm going to define now, I'm going to define what that row space is geometrically. Like, what is it? You know, it's not really geometric, but what is that? How do we define this row space? Okay. This row space is, and I'll use the phrase geometrically, this row space is a 2-dimensional subspace of R4. So what we'll do is we'll define the basis here utilizing the number of dimensions that are in the basis, okay, and the parent vector space. So it's a 2-dimensional subspace of R4, okay? And then if we look here, what we're going to have is the call space of A now. So we'll notice that our pivots are going to be in the first 2 columns. So our call space of A is going to be the first 2 columns in the original A. Okay, so this then is column 1 and column 2. That's going to end up being the call space of A. Okay, so what you'll do for the column space is you're going to say, okay, well, I'm going to take anywhere where I have a pivot in the REF of A, I'm going to translate that back up to A, okay? And wherever those pivots were, location-wise, that is in fact, those two columns are in fact the members of my call space. So the call space of A is going to equal then 2, 1, 1, okay, and -1, -2, 5. Okay. So the call space of A is a two-dimensional subspace of R3. And once again, just to emphasize, since the row space, since R4 requires 4 vectors, okay, 4 linearly independent vectors to get all of R4, what that means is that the call space of A is not R4. And since, the row space of A is not all of R4. Since we are required to have 3 linearly independent vectors to have a basis for R3, the column space of A is not R3 either. Okay, so in this case, we don't have enough vectors in either our row space or our column space to span any of our parent spaces, to span either R3 or R4. Okay, and that's just the truth. Okay, questions on that? Notice, 1, here is how you define the basis from the perspective of the vectors. Okay, and this is the description. So here's our description of the subspace. Call that a geometric description of the subspace. Okay. All right. How about this? Let's take, for example, we'll let A equal 2, -2, 1, 4 and 2, -3, 4. Find the row space of A and the call space of A. Give a geometric description of both. So I got the REF of A is equal to 2, 1, 4, 0, -4, 0. So there's the REF of A. So that means that the row space of A is equal to, all right, 2, 1, 4, comma, 0, -4, 0. So that's the row space of A. All right. This is a 2-dimensional subspace of R3. So that's a 2-dimensional subspace of R3. Okay. And then the call space of A is thus going to equal, okay, 2, 2, comma, 1, 3, which equals R2. So in this case, since it's R2, well, since there's 2 vectors, right, in the basis and both vectors are in R2, we can just define that as R2. Right, and so that is its geometric description. This geometric description is R2. Cool. All right, good. All right, so we'll finish up this section now, okay, with this. Is to notice something, right? Notice the dimension of the row space of A equals the dimension of the call space of A. So the dimension of the row space is going to equal the dimension of the call space of A. So in other words, if we write it dim, okay, row space of A equals the dimension dim of the call space of A. All right. Now let's talk about why. Okay. So we're going to say by definition, dim of the row space of A, okay, equals the rank of A. Now let's think about why for just a moment. The row space of A is defined as the number of non-zero rows in A, okay? Or excuse me, the row space of A is defined as the number of non-zero rows in REF A, okay? So its dimension is going to equal the number of non-zero rows in A. So let's write that down, okay? Dimension of the row space of A is going to equal the number of non-zero rows in A. And that is the rank of A. So we've got the number of non-zero rows in A, that's the rank of A. Convince yourself that that's the case, right? I mean, basically, yeah, those two numbers should be the same. Row space of A is the non-zero rows in the REF of A. Okay, the rank of A is the number of non-zero rows in the REF of A. Okay, there it is. Non-zero rows in REF A, excuse me. The dimension of the call space of A is the number of pivots in REF A. So that's going to be the number of pivots in REF A, right? Okay, you've got a row reduction. The dimension of the column space, right? The number is going to be, we're going to take the pivots in REFA and we're going to translate them back, right? So we're only going to take one vector in the column space of A for every one of those pivots, right? So there it is. So that dimension, the number of vectors in that basis is going to equal the number of pivots, okay? Well, the number of pivots in REFA, okay, will always equal the rank of A. Think about that. If we don't have a pivot inside of that row, okay, the row's got to be a zero row. So the number of pivots, right, is going to equal the rank of A, okay? And so so the row space of A, the dimension, excuse me, the dimension of the row space of A equals the dimension of the column space of A, which, by the way, equals the rank of A. Okay, so when I look at something like this, this is going to end up becoming really, really important for what we're going to do in the next section. In fact, hopefully, it'll make the next section really easy or easier. Okay, it's just to notice, right, that the basis constructed out of our linearly independent row vectors, right, is going to have the same dimension as the basis constructed from our linearly independent column vectors. Okay, and that is connected to the rank of A. All right. So, questions on that? Now what we're starting to look at, we're noticing how important that idea of dimension is, because it's actually super duper important. Okay, it's a very important idea. Okay, so now we're going to go into and we're going to talk about rank nullity. And rank nullity has everything to do with dimension. So here we have rank nullity. Okay. All right. So first, I want to remind you about what it means to be the null space of A. So the null space of A, okay, is a subspace of A defined as, okay, the set of all V belonging to V such that AV equals 0. In other words, it is the set of all solutions to AV equals 0. All right, so it's a set of all solutions to AV equals 0. So a couple things to get here. If the null space of A equals the 0 vector, okay, this means that the only solution to AV equals 0 is the trivial solution. So the null space of A equaling 0 actually implies that the whole set of solutions to AV equals 0 is just the 0 vector. And so if null space of A is just the 0 vector, then that means that the only solution to AV equals 0 is the trivial solution. Okay. On the other hand, if the null space isn't just the 0 vector, then we have other solutions to AV equals 0. So let's think about what the consequences of that are. Okay. For A, right? Let's first think about A, right? So let's suppose null space of A does equal 0. So let's say, for example, that the null space of A equals 0. So then, if that's the case, the only solution to AV equals 0 is the trivial solution. Let's add a wrinkle. Suppose A is square. So now we're going to suppose that A is square, right? So now we know something about A. A is square, right? And we now know that AV equals 0 is the trivial solution. So we added this extra wrinkle. What do we get from that? One, we get that A is invertible. That's the invertible matrix theorem. If A is square and the only solution to AV equals 0 is the trivial solution, then A is invertible. Awesome. Okay. What if it's, let's go back up here to just supposing the null space of A is equal to 0. We also get the column vectors of A are linearly independent. Okay, awesome. And, that's going to be the case if A is square. That's going to be the case if A is not square. All right, so notice that's why I actually put it back over in here, is to say, okay, we don't need for A to be square, right, for the null space of A to be equal to 0 to imply that the column vectors of A are linearly independent, right? These three come together no matter what. They are essentially the same statement, okay, or essentially the same idea, right? Solution to AV equals 0. The only solution to AV equals 0 is the trivial solution, and the column vectors of A are linearly independent. Those three, they're kind of like the same idea in many ways. They're connected. But if we get A as square, right, then we get A as invertible, right? A is square, meaning that there are, right, n vectors in Rn, in other words. That's what it means to have AV square. Okay, A is invertible. The column vectors of A span V, which oftentimes in the case will be Rn, right? Okay. Right, now we want to think, okay, they're going to span all of our n, right? I've got n of them. They're n linearly independent ones. They're also the column vectors of A will be a basis for Rn or for V, either one. We're going to talk about that. Kind of quasi the same, right? So we've got that they're now going to be a basis for Rn. So what that means then is if the column vectors of A are a basis for Rn, then the Colspace of A, which is the basis made up of the column vectors, equals Rn. But here's the other thing though, all right? So A is square. So you want to imagine A is square, all right? So like, let's say for example, I'm gonna draw a little picture here. So A is square. So like, let's say for example, I've got 4 columns, 1, 2, 3, 4 columns, and 1, 2, 3, 4 rows. I'm just using this as an example to show, same number of rows, same number of columns, right? So the column vectors, they're in R4. We already know that, right? Okay. But the row vectors are also in R4, right? The row vectors are also in R4. And because A is invertible, we know its row reduction is going to have, no 0 rows. No 0 rows because we know that A is invertible, right? So what that means also is that the row space of A is equal to Rn as well. It's going to equal the number of vectors. So the row space of A is equal to Rn, the column space of A is equal to Rn. And in fact, the row space and the column space, although they're not the same basis, they're going to give us the entirety of the same space. Okay, they're both in the same space, right? The same vector space, and there's the same number of vectors because we already talked about them having the same dimension, right? So they're basically going to give us different bases for the same exact space. All right. Now we can actually go in and we can expand on this. We can talk about things like if the null space of A is equal to 0 and A is square, we know that the column vectors of A are going to span. We said that, excuse me. We also are going to know that the that AX equals B is going to be consistent for all B. Okay, that's also going to end up being true. All right. We know that A will row reduce down to the identity. Okay, so what we're trying to do now, right, and I'm using the introduction to the null space is to show, right, okay, how these new ideas are going to connect into the old ones that we've been working with. Okay, we'll have all of these, like the invertible matrix theorem is now going to have like, I think 12 or 13 statements that are going to be all equivalent statements. Okay, all right, so now we have like this idea of the null space of A equaling 0, right? Let's actually go in and let's suppose, all right, we had A equal to 214, 0, negative 4, 0, okay? And we want to find the null space of A. All right, so this is just, again, a reminder of what we've been doing. We want to find the null space of A. So basically what that means to find the null space of A is solve AX, oh, that's not it. It's 4, 4, sorry, 4, 4, and it's that was A, my apologies. Okay, so we're going to solve AX equals 0. So go in and solve AX equals 0. So I took the REF of A, and that'll equal 102, 0, 1, 0, just in case, so you don't have to do a ton of computation right now. So use that now in order to find the solutions to AX equals 0. When you've got those solutions to AX equals 0, all right, okay, write the solutions in vector form. And then throw them up into the chat, please. So if I look here, right, we can actually imply that 0 vector. So essentially, my parameterization or my equations are going to be x1 plus 2x3 equals 0. And I have x2 is just going to equal 0. So we'll let s equal x3, or x3 equals s. So consequently, I'm going to get x1 equals negative 2s, x2 will equal 0, and x3 is going to equal s. So my vector, okay, my vector is going to be x equal to an s times negative 2, 0, 1. Okay. So what we're going to do then, okay, is we're going to say, okay, cool. So let's say then our null space. So that's the solution to x equals 0. My null space of A then is going to equal the set of all vectors v belonging to V, okay, such that V equals S times negative 2, 0, 1 for S belonging to R. And that's what's called our set builder notation. As a basis, okay, we can also just write null space of A is equal to negative 2, 0, 1. So we can actually just write that there. And there's an implication that what we're going to be doing is taking the span of all of those vectors. All right, just like when we write the basis for the column space, we write the basis for the row space, what we do is we essentially write, okay, so here are just my column vectors, right? And sometimes you'll see it written with like the word span, the span of these vectors, all right? So that's the entirety of the row space. Or we'll say the null space is this vector right here, okay? So if we write it as a basis and we say, okay, the null space of A is equal to this, there's an implication that what we're looking at is in fact a basis, okay? Now, what I want you to notice here is, so we have, right, I'm going to rewrite, well, first things first. What space is the null space of A in? What's its geometric description? What space is the null space of A in? Look at it, just tell me what that vector is in what space? What vector space?
R3.
It's an R3. Yeah, exactly. It's an R3. Okay. And we know that because there's 3 components in that vector. Okay. So the dimension, all right, so it's got a vector in R3, and we want to notice that the null space of A and the row space of A. Okay, so the null space of A and the row space of A form or are from the same space. So the row space is R3 and the null space is also in R3. And that's because basically the null space is going to be, we're going to think of it as a set of input vectors. Okay, so we've got this set of input vectors. We take the matrix A times the input vector in R3, okay, and we get out vectors in R2, all right? That's essentially what happens with this matrix A. So the row space, and we're going to see this inside of the next chapter, the row space is going to end up defining, right, like a chunk of what we call our domain, right? The domain, if we think about the matrix as a function, and the other chunk of the domain is going to be made up of the null space, all right? But we want to just notice that the null space of A and the row space of A are from the same space, okay? They're from the same space. And in addition to that, let's put them all together. So I'm going to have, I've got my row space. Sorry. And let's put the vectors together. Okay, so the row space of A was equal to 2, 1, 4, comma 0, 4, 0. All right, and the null space of A equal to negative 2, 0, 1. So those two, notice they're in the same space. Now notice also that there are 3 of them. There are 3 vectors here. So we've got 3 vectors here. If we combined the row space and the null space of A, would we get a basis for R3? All right, so we want to ask ourselves, if we combine the row space of A and the null space of A, will we get a basis for R3? There are enough vectors there. There are 3 vectors, right? So that's the right amount of vectors. 1, to possibly span R3. 2, to be linearly independent, right? There's not too many vectors, which would make it that we would not have linear independence. And there's not too few vectors that would actually allow us to not span. So it's possible. We got 3 vectors in R3, okay? So how am I going to go check? How will I check to see if this is in fact a basis? How would I check to see if these 3 vectors are going to be a basis?
Would you put them all into a matrix and then see if they're invertible?
See if that matrix is invertible?
Matrix.
Yeah. Right, okay. Everybody caught that? That's what we've done throughout the last couple of weeks, okay? Is, yeah, we're going to take those 3 column vectors So we'll take the 3 column vectors and form a matrix A. Okay, we're going to form this matrix A. All right. So we end up getting, we got 2, 1, 4, 0, 4, 0, negative 2, 0, 1 equals A. Or we'll call it maybe A star, because our original matrix was A. We'll form a matrix A star. All right. And then, like, so it is n. Yes, we have n vectors. Okay. A star. Right? And then the REF of A is going to equal 1, 0, 0, 0, 1, 0, 0, 0, 1. So the vectors of, okay, the row space of A and null space of A form a basis for R3. That's going to end up being really handy. It's going to be really handy when we talk about rank nullity. Okay, all right. It's going to be really handy when we talk about rank nullity. Okay. So here we go.
Oh, Professor, I had a question real
Let's
quick.
take, for example, yeah, what's up?
When you're writing down the row space and the
It's an
columns,
idea. Yes.
you write it down from the matrix A or the REF of A?
The row space and the column space, or the
Yeah.
null space? I'm sorry.
The
Say it
row
again.
space.
So for the okay, so for the row space, you're going to use the REF of A. Use the row reduction, the REF of A. For the null space, you have to use the RREF of A. So you've got a reduced row echelon form for A in order to find the null space. Okay, and for the column space, you can use either.
Oh, okay.
Yeah. So we use REF of A for the row space, and we use the RREF of A in order to find the null space. Okay.
Okay. Thank you.
So it turns out, you're welcome. Right. So let A, right? So we have a theorem. We're going to let A be an M by N matrix. Right? M rows, N columns. All right. So 1, we'll make the statement the null space of A. This doesn't need to be by definition. The null space of A is a subspace of Rm, right? It's a subspace of, no, Rn, excuse me. It's a subspace of Rn. Yeah, subspace of Rn. And the row space of A is a subspace of Rn. Okay, suppose that the row space of A equals V1 to the Vn minus k, and the call space of A, excuse me, not call space, but the null space of A equals Vn minus k plus 1 all the way up to Vn, all right? And those markers, I mean, they're not necessarily in any kind of order. It doesn't really matter. We don't really need an ordered basis here. We just need to know that basically when we have together the row space and the null space, they're going to add up to n vectors when we put them all together, okay? They form a basis for Rn. Put them all together, you get a basis for Rn. Okay? And that's what happens. So that's like another way to kind of help us think and put our minds around this rank-nullity theorem. All right? Is that if you take the row space of A, the null space of A, they're in the same space. You put their vectors all together and you end up with a basis for Rn. Okay? End up with a basis for Rn. All right? So what that helps us to do is it's going to help us to think through the rank-nullity theorem and maybe hopefully put together some connections. Okay, so we've got the rank-nullity theorem, and here's what it says. Let the column vectors of A let A be an M by N matrix. Okay. Then the rank of A plus the null of A, and I'll define that in just a second, will equal N, the number of columns. Where null of A is defined actually we should say is defined as the dimension of the null space of A. Another way to write this, or another way to think about this, so that's actually, this whole thing here this is rank nullity. That's the rank nullity theorem. Another way to think of this, all right, is something along the lines of this. The rank of A is the number of non-zero rows in A plus, okay, the dimension of the null space of A is going to be the number of free variables in AX equals 0. We actually already saw that that was going to equal the number of columns in A. We talked about that in an earlier lecture. So what rank nullity does is it basically combines this relationship and puts it into, instead of a systems perspective, right? Okay, it says, okay, what about from a vectors perspective? Okay, the rank of A plus the nullity of A equals N. We have the number of non-zero rows in A plus the number of free variables in AX equals 0 equals the number of columns in A. Okay, and that is the rank nullity theorem. There it is. Or Another way you can think about this is you can write it as the number of pivots in RREF of A plus the number of free variables equals the number of columns in A. You got that? So give you an example of how we might actually use something like this. All right, we'll let A equal 159 2610. There it is. What we're going to do now is we're going to confirm rank nullity. So we'll confirm rank nullity. And what that means is you're going to go find the null space of A, and you'll find the row space of A, or you go find the rank of A and then the dimension of the null space of A, and combine the two, and it should equal 3, because that's the number of columns in A. All right, so do that first. Write 1, find the rank of A. 2, find the null space of A. 3 will show that the two added together, the nullity of A, plus the rank of A equals 3. So take a couple minutes to do that. All right. So the RREF of A, or the REF of A, Actually, I'm going to take the RREF of A. There it is. The RREF of A is equal to 1, 0, negative 1, 0, 1, 2, and 0, 0, 0. So the rank of A equals 2. Okay. Now, I know actually that the null of A is going to equal 1 because there is one column in REF of A without a pivot, right? That's going to be the free variable. That's going to end up being in the free variable, all right? But what I want to do is I want to actually write out what the null space of A is. All right, so that's going to give me x1 minus x3 equals 0, and we have x2 plus 2x3 equals 0. So I get x1 equals x3, and x2 equals negative 2x3, okay? And so that means that x, I'm just going to use this. Hopefully you guys got to the point where you can do this. X is going to end up just equaling s times 1, negative 2, 1, right? And so the null space of A is going to equal the set 1, negative 2, 1, right? We'll just write it that way. And that means that the null of A is equal to 1. So that confirms that the null of A is equal to 1. We just found it. So the null of A equals 1. There we are. So rank of A plus null of A equals 2 plus 1, which equals 3, which equals the number of columns in A. So rank nullity has been confirmed.
So null A is equal to the dimension of the null space, right?
That is correct.
So can you explain how the dimension of the null space is 1? Because I thought the dimension was 3 since there's 3 components.
Okay. So the dimension of a space, the dimension of a subspace is equal to the number of vectors in its basis.
Mm.
Okay, the dimension of a vector space V is equal to the number of vectors in its basis too. But in order for us to actually construct a basis, right, for the entire vector space V, we are required to have the same number of vectors as we have components. So like the fact is that for like, say, for example, R3, we need 3 vectors in R3 to give us a basis, right? It just so happens that that is because those 3 vectors are necessary because of the number of components, okay? But that doesn't make the dimension of a space equal to the number of components. The dimension of the space is always equal to the number of vectors in its basis. So that's why, for example, we can have 2 vectors. If we have 2 vectors in R3, they're going to give us a 2-dimensional subspace of R3. Okay, the dimension of that space is 2. That's the number of vectors in the space. Okay, but the parent space in which it's in is R3.
All right, that makes sense now.
Okay, and so if we want to say this, we could actually say the null space of A is a 1-dimensional subspace of R3. It is essentially, it's a line. It's a line in R3, okay? It's a 1-dimensional subspace of R3, so it's a line in R3, okay? If it was a 2-dimensional subspace in R3, it would be a plane in R3, though, from a geometric perspective. It's a great question, right? There's a lot of things to parse out here, okay? There's a lot of things to parse out here in terms of language, all right? And you know, hopefully I've demonstrated the difficulty that can be had when trying to say things, right? Versus even trying to write them. Another good reason to actually go do this one is an open note, open book test, okay? But what you want to do is you want to like really, as you're working through the homework and as you're working over the weekend, what you want to do is you want to like make sure that you're making those kinds of distinctions. The distinctions that have everything to do with details, okay? Because the details do matter, all right? Like that particular detail that Alex, yeah, that Alex just stated, okay? All right. Any questions on that? Okay. So there are videos on all of these things. You've got some homework to do over the weekend. And go in and there's a video on the invertible matrix theorem. We've talked quite a lot about the invertible matrix theorem. Actually, let me just, yeah, we've talked quite a lot about the invertible matrix theorem thus far, and how it applies now to vectors, okay? And